previous module, I talked about the radial wave function part of the hydrogen atom, and also we started with the angular dependence of the wave functions of hydrogen atom. And where I left you was the point where the angular dependence of s orbital wave function, and I said you that for any s orbital, whether it is 1s, 2s, 3s, 4s, the wave function does not have the angular part of the wave function does not include theta and phi functions. So if it does not include theta and phi functions, then obviously it is theta and phi independent, angle independent, and then the only structure, only shape which is possible for s orbital is a spherical shape. Okay, because you have the probability, if you go from origin on any side, the probability at a particular distance will remain same. So s orbital is spherical, and this spherical symmetry arises because the angular part of the wave function does not have theta and phi. So this up to this we did, and then if you look at the radial part of the wave functions, which I did earlier also, for a 1s orbital you have exponential minus r divided by a naught is the only part, except some constant, that is 2 1 multiplied by 1 over a naught to the power 3 by 2. So some constant multiplied by the radial dependence is shown by exponential minus r divided by a naught for 1s. For 2s you see that you have the radial dependence is 2 minus r divided by a naught, and then exponential minus r divided by 2 a naught. For 3s you have the dependence 6 minus 6 rho plus rho square exponential minus rho divided by 2. So this we have already seen in the previous, you can check, and I did it in details in the previous modules also. Okay. So if we combine the radial part of the wave functions with the spherical harmonics, what do you get? Because the total wave functions will be, I said you, this r part, theta part and phi part are the component wave functions. So whenever you have a wave function which is dependent on more than one variable, you split that wave functions into components, and then when you write the total wave functions, it is the product of the component wave functions. So here I have tried to combine all these theta part, phi part, that is the spherical harmonics, together with the radial part, and that will be the total wave functions. And now if you want to write that total wave functions, now you designate this as psi 1 0 0. All the three quantum numbers you will write psi n, l and m will be the total part, and this will be a combination of r, which depends on n and l, then theta, which depends on l and m, and then phi, which depends on m only. So the total wave functions will be a combination of r n l, theta l m and phi m, and the representation is psi n l m. So when I am writing psi 1 0 0 means n is equal to 1, l is equal to 0 and m is equal to 0, so obviously it is 1s orbital. When I am writing 2 0 0 means it is n is equal to 2, l is equal to 0 and m is equal to 0, so it's obviously it is 2s orbital. So if you look at the combination, the only spherical harmonics which we have for is 1 over root under 4 pi. So this YLM for all these functions is 1 over root under 4 pi. So what will be the change? The change will be in the constant part only. Rest of the part, radial part, will remain same, exponential minus r divided by a naught, 2 minus r divided by a naught, and then 6 minus 6 rho square exponential minus rho divided by 2, and you know rho is equal to 2zr divided by n 0. So these things I am repeating time and again because in a naught, and where a naught is Bohr's radius, because if you watch it time and again it will be in your mind. Okay, so it's Bohr's radius. Now if you look at these functions, again radial part tells you that the psi 1 0 0 decreases as you go away from the r. 2 minus r divided by a naught means at any value of r, that is r is equal to 2 a naught, psi 2 0 0 will become 0. So function will be 0. And if r is greater than 2 a naught, if r is greater than 2 a naught, then what will happen? This function within the bracket 2 minus r divided by a naught will become negative, and the whole function will be negative. So as you go away from the nucleus, at a particular distance, the function goes on decreasing because it's exponentially decreasing. So it goes on decreasing, but at a particular distance, when r is equal to 2a naught, the function becomes 0. And beyond that distance, r is equal to 3a naught, 4a naught, what will happen? The function will be negative function. Okay. So if you look at the 300 functions, 300, then you have a constant part, then you have a quadratic equation, 6 minus 6 rho plus rho square. This quadratic equation means that there are two values of r at which this function will be 0, and you will have two nodes. And if you put these values, what you will find it that initially the function decreases, it becomes negative, and then again it becomes positive. Okay. So if you look at this one, psi 1001s orbital, we say that pre-exponential factor is constant. There is no pre-exponential factor. It's 1 only. Okay. So variation depends on exponential part only, and then electron density is highest at the center, and electron density decreases as the distance from the center increases. So the function decreases sharply as you are looking at psi 100 square. So it decreases very sharply, and electron density becomes 0 only at infinity. So only at infinity the electron density will be 0. So this tells you, this particular diagram tells you both radial dependence as well as angular dependence, because you look at this one, a spherical symmetry I have drawn, and then at the origin the density is highest, so the color is also more dark. If beyond that the color is a little lighter, showing that electron density decreases, then further lighter color, electron density decreases, and there is no node drawn in this diagram. Okay. What happens to 2s orbital? 2s orbital, I said you that pre-exponential factor predominates at shorter distance. At very small distance, pre-exponential factor dominates, and then gives rise to the idea of the position of the nodes. So it gives, here we have a node. I said you r is equal to 2a naught, we have a node. So I have written it also. Exponential factor controls the shape of the curve at larger distance. Point at which radial wave function becomes 0 is called node. It is a point where r divided by a naught is equal to 2, means r is equal to 2a naught. So when r is greater than 2a naught, the function becomes negative. So you see the function is positive here in this region, and function is negative here. Okay. At very large distance, the curve runs parallel to the x-axis like this one. Okay. And if you plot this square of this function, then you have a positive only positive part. Negative part, if you square it, it will become positive. Now you see a black line within this I have drawn here. This black line, this black circle tells you that it is a node. Okay. So we have a node here in this function. You have a positive function, and then it becomes negative function later on. Okay. So we have a positive part, we have a negative part. I have merged this last figure with the spherical angular dependence also. So this graph is both angular dependence also and radial dependence also of the function, it tells you. Okay. So this is how you can interpret the wave functions in the physical terms, and that you know that 1s has no nodes, 2s has one nodes, 3s has 2 nodes. So that's already known to you. Now the only thing is that we are explaining those facts which you were taught at earlier levels without giving any explanation. You were asked to believe that s orbital is spherical. You never asked the question that why is it so that s orbital is spherical? Why should you believe it? Now you know the answer is that the angular dependence of the wave function or spherical harmonics of the wave function for s orbital does not have theta and phi function. So s orbital is spherical in shape. So the fact was known to you. Explanation we are learning now through the quantum mechanics. Okay, through quantum application. So same way for 3s orbital, you have two different nodes. First node 1 is this one, and node 2 is this one. So you have two different nodes in the 3s orbital, and same way you can go for other orbitals also. Okay, if you go for a probability distribution function, then what we see that if you look at the radial part, we don't believe in only any one direction. We have to talk about the spherical probability in a spherical shell, because if you say the radial probability, this is the radial probability and this is the radial probability for 2s orbital. Okay, then radius, if you have the polar coordinates, if you have the polar coordinates like this one, okay, these are polar coordinates, and suppose you are looking at a particular distance from the origin and this distance is r, then this r distance from the origin is not in one direction. It could be theta, could be this value also, it could be parallel to the z-axis also, it could be parallel to the x-axis also, it could be parallel to the y-axis also, it could be in between x and y also, and all is r distance, same distance, r distance. So when we are talking about a probability or a function at our distance r, then we have many such lengths in all possible direction. So it will not be one particular orientation, it will be around this origin in a it will form a ring, and that not to say ring will be two-dimensional, it will form a shell. Believe consider it, imagine just two spheres put one within other, a large sphere and a small sphere, so that in between you have a small space which is vacant, everything. So that small space which is around the smaller sphere is called the spherical shell, and the volume of the spherical shell is 4 pi r square dr. So this r which you can measure here, 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 this r, then you can talk about the probability in all possible directions of the origin point. Okay, so we are more interested in radial probability distribution function rather than plotting the r function, only the r function. Okay, so if you have to calculate the radial probability distribution function, then you take the radial part of the wave function r square, and then your volume element is 4 pi r square dr. Okay, so this is called radial probability distribution function. Now this represents the distance from the nucleus at which the electron is most likely to be found, independent of direction. When you draw r in one particular direction, then you are fixing the theta angle also, so the distance is fixed. But when we are calculating the radial probability distribution function, then what you are doing, it is independent of the direction. Theta could be anything, phi could be anything. Okay, so you have all the r possible, all the r possible from the origin, you include that. And if you have to find out this radial probability distribution function and the maximum probability of the electron away from the nucleus, then what you calculate, you differentiate this radial probability with respect to r, this probability distribution function with radial probability distribution function with respect to r, and equate it to 0. Okay, and if again double differentiate, and if it is less than 0, then you say that p is of the real value, probability has maxima. Okay, so for maximum probability, if you do this calculation for 1s orbital, then what do you find? You have 4 pi r square, then 1 by pi a naught to the power 3 a naught raised to the power 3 raised to the power 1 by 2 exponential minus r divided by a naught square. This is probability distribution function p. So this probability distribution function, which is actually, if you multiply everything, and then 4 divided by a naught raised to the power 3 r square exponential minus 2r divided by a naught. So this is your probability square of r NL r square 4 pi r square dr. Okay, so this p we have determined. Now you differentiate this p with respect to r. See, it's a square of this one, so exponential minus 2r divided by a naught. Okay, and a square of this also, so it will be 1 by pi a naught to the power 3, and 4 pi r square is already there. So finally what you get is 4 divided by this pi, and pi will go. Okay, and then you have r square exponential minus 2r divided by a naught is the function, and 4 divided by a naught whole cube is the constant. So if you differentiate, you have a constant 4 divided by a naught to the a naught raised to the power 3, and then the function has two parts. One is r square, another is exponential minus 2r divided by a naught. So differentiate this one, 4 divided by a naught, then first differentiate r square, you get 2r, then you keep the exponential minus 2r divided by a naught constant, then keep the r square constant, and then differentiate exponential minus 2r divided by a naught. So minus 2 divided by a naught, it will be exponential minus 2r. Okay, and if you do this, you get this equation. And if you equate it to 0, dp divided by dr equate it to 0, then we can write 1 minus r divided by a naught is equal to 0. So if for this equation to be valid, if it is equal to 0, then either this is 0 or this is 0. This is 0 means everything will be redundant. So 1 minus r divided by a naught is equal to 0, and hence r is equal to a naught, and a naught is what? Bohr's radius, which is 0.529 angstrom. And that's what you say, that in a hydrogen atom, the if you calculate the probability for 1s atomic orbital, the distance which comes from the Bohr's atomic model is 0.529 angstrom. Okay, so exactly the same thing we got here also. Okay, so the point of maximum probability is first Bohr's radius, that is r maxima is a naught. At nucleus, what will happen? R is equal to 0, so r square will be 0 and probability will be 0. Okay, at infinity, what will happen? Exponential minus 2r divided by a naught is equal to 0, so the probability is also 0. So this particular function, that is 1 by pi a naught whole cube under root exponential minus r divided by a naught function, which we get for RNL. This is your RNL. Okay, this function explains the existence of 1s atomic orbital at a distance of 0.529 angstrom as obtained in the Bohr's model also. Okay, so this and this also explains that why electron is not present at the nucleus. This also explains that why the probability of finding the electron at infinity is 0. Okay, so radial probability distribution function is an important quantity in hydrogen atom. We are explaining everything which is known to you through quantum mechanics, already known to you at your earlier level, at undergraduate level. You have already done these things. Okay, if you look at the 2p orbital, what happens? What is the probability? You see, for a 2p orbital, the point of maximum probability I have calculated, and then it is 4 pi r square. Okay, everything, and what you get is, finally just differentiate dp by dr and equate it to 0. So what you have is 4r cube minus zr4 divided by a naught is equal to 0. Okay, so and if you equate it to 0, what you get? R maxima is 4 a naught. That is equal to 1 for hydrogen atom. Okay, so R maxima comes out to be 4 a naught. And what is the node? Where is the node? Okay, can we calculate the node here? It's for 2p orbital. Okay, so for 2p orbital, for R maxima for 2p and R maxima for 1s, we have found is only one a naught. Okay, so this way you can calculate it for other orbitals also, for 2s also, for 3s also, and everything. Okay, and but for 2s, you know that at r is equal to 2 a naught, it will have a node. Okay, that you can do. Now plot of a spherical harmonics of 2p orbital. This is the radial part of the 2p orbital. A spherical harmonics of 2p orbital, if you want to plot, then what do you have? for 2p function, means 2p function n is equal to 2, L is equal to 1 and m is equal to 0 plus minus 1. So the spherical harmonics is root 3 by 4 pi cos theta, root 3 by 8 pi sin theta exponential I phi, and root 3 divided by 8 pi sin theta exponential minus I phi. And in the earlier lectures I said you that since this is an imaginary function exponential I phi and exponential minus I phi, so we cannot physically interpret this function. In order to interpret this function, we have to convert this into real function. And one way of converting this is taking a linear combination of these two orbitals. And I derived this also in the earlier slides. If you go back in the previous modules, you will find it. Linear combination. And we say a positive combination and negative combination we write as psi 1 plus and psi 1 minus, and which comes out to be root 3 by 4 pi sin theta cos phi and root 3 by 4 pi sin theta sin phi. Okay. So we have three functions, real functions. One is root 3 4 pi cos theta, another is root 3 4 pi sin theta cos phi, and the third one is root 3 4 pi sin theta sin phi. Okay. And if you want to see this angular dependence of these spherical harmonics 1, 1, 2 and 3. So see, now we are not interpreting y0 plus 1 and y0 minus 1. We are not interpreting this function, we are not interpreting this function. Rather, we are interpreting the linear combination of these two functions. Okay. So if you interpret this, what do you find? If you look at it's everything is given. So whether it doesn't matter whether you have done mathematics at earlier level or not. Okay. I have given you sin theta, even sin theta, cos theta values also. Okay. So that should not be an issue with you. Okay. Now you see, on a positive z axis, theta is equal to 0 degree. So cos theta is plus 1. In xy plane, it is the xy plane is drawn like this one. Okay. So in departure from the diagram given in the book, here normally what you do, you make this axis you will find this axis as the x-axis and the s-axis as the y-axis. Normally in the book, YZ plane is the plane of the book, plane of the page. Now here what I have done, I have just to make it more easier for you to understand, I have made XZ plane as the plane of the board. So that now you have all the theta angles varying from 30, 45, 60, 90, 120, 135, 150, 180 in the plane itself. Okay. Otherwise, it would have been in the perpendicular plane. So now it is easier for you to see that in the xy plane, theta is equal to this, and now xy plane is a plane which cuts the board into two on the x-axis. Okay, this is your xy plane. So in this plane, theta is equal to 90 degree, and at this plane, at this point, so in this plane, since theta is 90 degrees, so cos theta will be 0, and on the negative z-axis, theta is 180 degree. So it has a cos theta is equal to minus 1. So if you plot a function y10, what you get? You get a positive lobe on the positive z-axis and a negative lobe on the negative z-axis, and in the xy plane the function is 0. It means angular node will be in the xy plane. So this will be an angular node. Xy plane is an angular node because the function is 0 there. And its function is 0 because the function depends on cos theta, and theta is equal to 90 degree. And so cos theta is equal to cos 90 is equal to 0 degree. Okay. Okay. So this is how. So what we say, y10 belongs to pz orbital, and we say pz orbital because we have a positive lobe on the positive z-axis and a negative lobe in the negative z-axis. Okay. What about the other functions, which is a linear combination of two spherical harmonics, psi 1 plus and psi 1 minus. Okay. So a linear combination is sin theta cos phi. It's a constant plus sin theta cos phi. Now you see, it's the same diagram. XZ plane is the plane of the board, okay, and your this is your XY plane. This this ellipse is an XY plane. This is an XY plane. Now you see, along the positive and negative Z axis, what will happen? Theta is 0, positive axis and negative axis is 180. So sin theta will be 0. Sin 0, 0. Sin pi is also 0. And what does it mean? It means this sin theta is 0, so the function will be 0. Along the positive and negative axis, this function y1 plus will be 0 as sin theta is 0. Along the positive and negative y-axis, what will happen? Along the positive and negative y-axis is this one. Okay. So y-axis is this one, perpendicular to the plane of the board passing through the origin. Okay. And here also the function will be 0 on this axis also. So along the y-axis also the function is 0. Hence the YZ plane, you see, along the z-axis the function is 0, and along the positive and negative y-axis the function is 0. So YZ plane is the function is 0 and it will be the nodal plane. You see, you contrast this one with the previous one. Here XY plane was the nodal plane and here angular nodes. So XY plane is the nodal plane where probability is nil. In the case of y1 plus psi 1 plus, which is a positive combination, YZ plane is this plane. Okay, so this plane the function is 0 and it is the nodal plane. Along the positive x-axis, now see, along the positive x-axis cos phi is equal to plus 1 because phi is equal to 0. That you know. If you remember your original diagram, this diagram is just for making you understand the things. This was your x-axis, this was your y-axis, this was your z-axis, and then this was your r. So if you draw a perpendicular here in the xy plane and then you combine this with this one, this angle is called phi angle. So this along the x-axis phi is 0. Along the positive x-axis phi is 0. So cos phi will be plus 1. And what will be the value of sin theta? Sin theta will also be plus 1 because this is again a perpendicular to this one, okay, and it is a 90 degree. So sin theta is also plus 1. Therefore the function is positive on the x-axis. And along the negative x-axis cos phi is equal to minus 1. So what happens along the negative x-axis? If it is 0, then after one complete rotation, after pi you go to the minus x-axis. So cos phi becomes minus 1 and sin theta becomes plus 1, and therefore the function is negative again. So you have a positive lobe on the positive x-axis and a negative lobe on the negative x-axis. Okay. Again, this fact was known to you. You say that px orbital is one where the lobes in the x and x direction. Py orbital is one where the lobes are on the y-axis, and pz orbital is one where the lobes are on the z-axis. So we are getting the same thing. We plotted the cos theta function and we got pz orbital. We are plotting sin theta cos phi and we are getting px orbital. But the difference between the two is that the YLM or spherical harmonics of z orbital is the one which you obtain root 3 by 4 pi cos theta. But the spherical harmonics which you get for magnetic quantum number plus 1 or minus 1, we cannot interpret. So we take a combination of these two in order to get the px and py orbital. So if you plot py orbital again in the similar way, what you get? Along the positive and negative z-axis, this function sin minus 1 becomes 0. Along the positive and negative x-axis, the function becomes 0. So here the nodal plane is xz plane. positive and negative z axis, the function is 0. Same way, same angle, it's already there. You have everything in this diagram. So along the positive and negative axis, the function psi 1 minus, which is a combination of, again, negative combination of psi 1 plus 1 and psi 1 minus 1. And I said you in the earlier lecture that we multiply it by I divided by root 2, or 1 by or minus I divided by root 2, and how to arrive at this combination and the value. It's in the earlier slide. You can go and see them. Okay. So sin theta sin phi function is 0 in the xz plane, and we say xz plane is the nodal plane for py orbital. Okay. Along the positive y-axis, sin phi is equal to plus 1 and sin theta is equal to plus 1. So the function is positive. So along the positive axis, along the positive y-axis, this will be positive function, and along the negative axis, this will be a negative function. So whatever you write, when you start writing your p orbital with boxes like this one, and you write minus 1, 0, plus 1, and then you write px, py, pz, then you are wrong. Py is not magnetic quantum number 0. M is equal to 0. M is equal to 0 is giving you y 1 0, and y 1 0 is proportional to cos theta, and plot of this has given you pz orbital. So whenever you write magnetic quantum number, you don't write this designation, then you are right. Okay. And whenever you write this designation, then you don't write the magnetic quantum number. Both if you are writing, then the problem will not be in the at least z orbital, because what will happen, this you can make this as z orbital. Okay. So you remove this py and you say this is pz orbital, and this you write as py orbital, but this also you cannot do, because you know that px and py function are not the magnetic quantum number minus 1 and magnetic quantum number plus 1. It's a linear combination of these two, a positive combination and a negative combination. A negative combination gives you py orbital, and a positive combination gives you px orbital. So it's not, if you are saying that minus 1 magnetic quantum number is giving you px orbital, or plus 1 magnetic quantum number is giving you py orbital, then you are not correct. Okay. A linear combination of magnetic quantum number minus 1, y1 minus 1 and y1 plus 1, a linear combination gives you px and py orbital. Okay. So these facts were known to you earlier, but now we have explained it through the radial part and the angular part of the wave functions. Okay. So almost we are through with the hydrogen atom. We started with hydrogen atom as writing the Schrodinger wave equation, and then through power series method using Laguerre polynomial and associated Laguerre polynomial, we derived the radial part of the wave function. We after separation of variable, you got phi and theta equation and R equation. Phi and theta equation, I did not go into the detailed solution because it will be repetition, and we have already done it in the rigid rotor. The same solution is for the hydrogen atom also. Okay, because the same equation you get here, and then radial part of the wave function solution we did in details, and then we tried to interpret the radial part of the wave functions as well as angular part of the wave functions, which together is called as spherical harmonics, and we got the shape of the different orbitals. We can further go and do the same for the 3D orbitals also, that how do we get the what is the plot of 3D wave functions, and how do we get the different d orbitals. But if the time permits, I will take it up at the end of the this one, and or if the time permits, we will do it again. But for the time being, for the hydrogen atom solution is complete for this module. Okay, thank you. Okay, so till now what we have done, we have plotted the eigenfunctions. if you look at the energy eigenvalues of hydrogen atom, then what we can do is that we already know that this function we know, n is equal to lambda is equal to L plus 1 plus Nr. Nr is called radial quantum number. I said you earlier also, it could be 0, 1, 2, 3. While L plus 1 we say N, and N is called total quantum number, and N is principal quantum number. So it's not total, it's principal quantum number. Okay, principal quantum number, and its value is 1, 2, 3. So if you put the value of lambda, which is 4 pi a square mu e square h square divided by alpha, then alpha square and alpha square is equal to minus 8 pi square mu e divided by h square. Then what you can write? You can write lambda square and n square. Lambda and n is the same thing. Okay. Then energy value you can calculate, eigenvalue you can calculate, and this eigenvalue comes out to be minus 2 pi square mu e raised to the power 4 n square h square. So it's the same value which you obtain from the Bohr radius, and you say it is minus 13.6 electron volt divided by n square En. This you already get in Bohr's atomic model. Okay. So applying Schrodinger wave equation gives you an eigenfunction, a plot of which explains all the known facts about the orbitals. S orbital is spherical, p orbital is dumbbell, p orbital has 3 different kinds, px, py and pz, and how it is plotted. Okay. And also we saw that for 1s orbital, the point of maximum probability comes out to be a naught, which is Bohr's radius, and that's 0.529 angstrom. So the radius of the 1s atomic orbital is the same as you got in Bohr's atomic model, and we got the energy eigenvalue also same as we got in the Bohr's atomic model. So by applying Schrodinger wave equation to hydrogen atom, and what we did, we separated the variables into r, theta and phi in the spherical polar coordinates, and then I said you that theta and phi functions are same as we did in the case of rigid rotor. So we did not go into the detailed solution, and we borrowed that solution from the rigid rotor module. And our equation, since we did not do so, our equation we did in details in different lectures. It's a lengthy calculations, lengthy derivations involving Laguerre polynomial and associated Laguerre polynomial. And then after getting the functions, I tried to give you a physical explanation of the equations. And all those physical explanations which I have given you was already known to you. You were knowing that s orbital is spherical, you were knowing that 2s orbital will have a node, you were knowing that 3s orbital will have a node, but why it will have one node? Why it will have 3s orbital will have 2 nodes? So all those, why s orbital is spherical, all those explanations and the physical picture of the equations I have given you. I hope I have given you a full understanding of the quantum mechanical results of hydrogen atom solution of the Schrodinger wave equation. So up to this, we did different problems of the different model system as well as the real system in the quantum mechanics. We applied Schrodinger wave equation, we got the energy values, eigenvalues, and we got the eigenfunctions. We tried to explain those mathematical equations in the physical terms also. Okay. Beyond this, we will go for other systems and we will see how quantum mechanical deals with the other system. For the time being, for this module, this much is enough. Okay, thank you.